also record it before I forget. I welcome you, Romain Laugier. He's a new postdoc in the team of Denis, working on the ERC sci-fi projects. And before coming to Leuven, he did his PhD at the Observatoire de la Côte d'Azur. And Romain, the floor is yours.
Thank you very much. So thank you for this opportunity. My name is Romain Laugier. I'm going to talk about most of the work I did in the Kernel team, trying to push the performance of kernel phases to the high contrast domain and to the direct detection of exoplanets. And now this is not working anymore. Yeah. A problem already. Okay, so we all love exoplanets, right? So it's a very exciting field. But we also love complaining about how hard they are to detect, right? And we usually do that talking about lighthouses and fireflies. But the truth is, it's a combination of two factors. The first one is the contrasts. You have usually at least 10 to the 4 to maybe 10 to the 9 contrast between the star and the planets, and also the very small angular separation between the two. So that's why most of the planets so far have been detected through indirect methods like transit and radial velocity. But we do have a few detections, direct detection through that we've done recently. And those are really, really important and really, really interesting because they provide us with some of the spectra of these planets. And these give us information on the temperature of the planets and the atmosphere conditions and their composition, etc. But it is also very, very difficult because we are actually observing those stars and planets with telescopes of finite dimensions. And it's the dimension and shape of the apertures of our instruments that define the size and shape of their point spread function. And in turn, it rules the distribution of light, and it dominates the distribution of light in the images we are trying to take of these planets. And the characteristic dimension here is lambda over d, the diameter of our telescopes. And for the case we'll be most interested in, it's going to be for the 8 meters telescope observing in the near infrared in the H-band. So for the H-band with the 8-meter telescope, this lambda over d is at 40 milliarcsecond. That's what we call the diffraction limit. And compared in angular separation to the current detection of planets, this is where we are. So most of the direct detection have been done at separation that are significantly larger than that. Even for the very young and massive planets, which are easier to detect like this, we are typically at least detecting them at 5 lambda over d, 10 lambda over d, something like that. And the reason behind that is that lambda over d cannot be this simple, the resolving power of our instruments, its capability to distinguish between the lights of two objects cannot be really described by this single number. Instead, what we can do is think of it in terms of signal to noise, right? So for a star here, if you consider a planet that would be, for example, around here, its signal to noise would be the light from the planet divided by and now I don't have animations. That's fantastic. Again, one more time. No. This used to work perfectly. Okay. So I'm gonna try doing that through different software. Sorry, last minute hack here. Okay, let's stop that for a second. It worked perfectly yesterday. So let's go back up there. So yeah, for a planet that would be located here, you'd have the photon noise from the light that is in the diffraction pattern from the star. Okay, and also you would have the contribution of the variability of this point spread function that is due to wavefront errors in the pupil mostly. And so the go-to approach to fight this problem has been to focus on the photon noise with what we call coronagraphs. Coronagraphs are complicated instruments that place a mask in an intermediate image plane. And this mask is going to actually break the convolution relationship between the object and the image and give a special treatment to the light that is on axis, that is the starlight. And so it will basically turn off the light from the star and let the light of the planet pass through. We are now able to build these coronagraphs for very small inner working angles, basically almost down to lambda over d. The problem is that the smaller the inner working angle, usually the more sensitive and the more vulnerable they are to wavefront errors. And so we are even using state-of-the-art adaptive optics, measuring the wavefront and correcting it through with deformable mirrors. We cannot produce a perfect wavefront. We will never be able to produce a perfect wavefront. And so what you can see here in some of these coronagrams that are that provide very fantastic views of this stellar system, of these planetary systems, is that when you get closer, so you have to realize that these separations that you have here are significantly larger than lambda over d, right? And if you get at smaller separations, your capability to detect a planet is really dominated by what we call this speckled noise, that is this variability of the PSF, right? And to tackle this speckled noise problem, one thing that you can do is go back to some of the methods that were developed in the 19th century. And that's the biggest example of that is masked pupil interferometry. In this case, what you would do is put a mask in front of your aperture and let the light go through only through 2 holes, for example, in this case. And doing that, you transform your PSF from this into something that looks a lot like a set of fringes. And so now we have more complicated masks that produce a larger number of fringes, but the idea is that those masks are non-redundant, and so the different sets of fringes that you have inside the image can be read independently in the Fourier transform of the images, both in amplitude and phase. And when you add a companion here, there is a very obvious one here, you will see the signature of that in both your amplitude and phase, in full pupil and masked pupil. And then when you add aberrations on top of that, The idea is that with the masked aperture, the wavefront error behaves as piston in each of the holes, which is going to shift the fringes, move the fringes around, but not change their contrast or their amplitude. On the other hand, the phase of the fringes is directly affected. But it turns out that it is possible to recover a large part of the information from this Fourier phase. And you can do that using closure phases. So here I describe closure phases in the framework that we use in the same framework that we use for kernel phase. So what we do is we build a vector phi containing the values of the phases that we extract from this Fourier phase, from this Fourier plane. And these can be compared to the astrophysical phase signal phi O here, plus a contribution brought by the aberration. And this contribution can be linear, can be described by a linear transformation from a vector small phi here that describe the lists here of piston errors in phase in all of these holes, right? And so to cancel out this aberration, one thing that you can do is build a matrix C that satisfies CA equals 0. And then by multiplying your whole equation with that, you'll be able to cancel this term altogether. And so the classical way to do that is to do closure phases where you actually select the pupils, your subapertures that build triangles like that, and by summing up the different baselines, the phase of the different baselines that correspond to this triangle, you are going to build one closure phase. And you can do all the different triangles, and you will build this, like putting them into a matrix that will give you your matrix C. So that's one way to compute these closure phases. What's interesting is that now with adaptive optics, we can get into conditions where the wavefront errors are small enough that even in your full pupil domain, the behavior of your Fourier phase here stays actually pretty consistent with what you would have in a masked array interferometer, or in any interferometer for that matter. So what we do in kernel phase, we rewrite this same equation, but taking into account that the matrix that translates the pupil wavefront error into Fourier phase has this redundancy term on top of it. And you can then the kernel matrix here that you have to build to satisfy this equation is a little bit more complicated. We build it through SVD. But apart from that, the other thing that you have to do is construct a discrete model that represents your aperture as if it was a very large series of small subapertures. And this will give you a very dense sampling of your UV space, as dense as you want to make it. And so these K-phi observables are what we call the kernel phase. And we call here in what I'm going to show, I call these the robust observables, and I call them with the vector kappa. And so then we can do what we can do with this kappa is to do model fitting. Basically, that's most of what we do. So we are going to compare the kernel phases that we measure after calibration, of course, to the kernel phase of a model. And for example, here it's for a binary model the model that correspond to a binary star. So we leave behind these pretty images and get only a set of observables. But in this case, you can see that we are pretty sensitive in what we can detect because there's actually a companion here. We also have tools to have more user-friendly results from that. And the one I especially like is what I call a collinearity map. It corresponds to a match filter of the presence of the binary companion at any given position. So each pixel lights up whenever the signal that we measure corresponds to the presence of a companion on it. And so you can see here that there's a companion here that wasn't really visible, but is really obvious in the collinearity map. And so this helps you suppress your speckle noise in your data. But what you're left with is photon noise. And then we take that into account in a statistical way, right? We compute the covariance matrices, and we use that to do a whitening of the data and remove the correlations in the data, and we can then build detection tests that we can predict the sensitivity of. And so these are an example of that. So we do have two different approaches on our hands. The first one I showed was the chronographs that tackled the photon noise, and then I showed the kernel phases that tackle the speckle noise. But we cannot really combine the two because of the chronograph break the convolution relationship, and that wouldn't make sense to process data in a Fourier transform when there's no convolution relationship. So the different approaches that I used were the following. The first one was to improve the performance and the sensitivity by improving the accuracy of the kernel phases. Then I played around a little bit with fixing the convolution relationship and extract kernel phases. Then I also try alternative starlight suppression techniques. And then I'm going to show that there was a kind of a change of plans, and we played around with the idea of modifying the instrument completely to kind of have be able to do both things at the same time, but you'll see that. So I talk about some of the measurement errors. So usually we can classify these in two categories. There are the fast evolving errors that contain mostly your detector noises, right? And theoretically the speckle noise we remove with kernel phases. And this is going to be taken care of in an analytical way. And they enter into the variable the vector that I call epsilon noise. And then you have your slow moving errors that are going to generate biases. They come from a large number of sources, of course, but usually you take care of them in calibration. And we call this part of the residual epsilon cal. So in terms of calibration, it's no different than any other science observation. Usually what you do is observe your science targets, and then you try to observe in the exact same condition a target where you expect to find no astrophysical signal. And then subtracting the two, you can remove your bias, and you'll be left with only your statistical error and your astrophysical signal. But it's very difficult both to ensure that the astrophysical signal is zero here, and that your observing conditions stay the same, even though you have to open your AO loop, point again to a different target, then close your AO loop again. this is rarely the case. So in high contrast imaging, they've been using angular differential imaging. So that's a technique where you make use of the field rotation in your data. You acquire a series of images with this field rotation, and you compute a common reference based on these images that you're going to subtract from all of these raw data. Then you derotate and realign all your images, and then by stacking them, you can reacquire some signal to noise and remove your bias. In kernel phase, this would be really difficult to do because you cannot really derotate a kernel phase vector, right? So instead, what can you do? You can observe your same targets at different points in time, like with different field position angle. And then by subtracting those two, the bias should be the same. And by subtracting those two, you can remove your bias, and then you'll be comparing your differential observable to a differential model that you'd have to compute in working with that. But this only works with 2 frames. What I really wanted to do was build something that was much more flexible. And to do that, what I suggested was to build a vector that would be the concatenation of the series of vectors that you extract from a series of images. And so you work with a single vector that represents your whole sequence of observations. And then the bias signal applies on that simply by being replicated on each part of the vector. And the effect of that can be reproduced by using a very simple UF matrix here. And you can see that one solution to get rid of that is basically the same as what we did with kernel phase. Would be to build the matrix L that satisfies LUF equals 0. One way to do that is to compute a projection. So that's what I suggested. So here, for example, to show that graphically, if your kappa S observable span this whole 3 dimensions, and your vector of epsilon cal, the vector spanned by your bias was only this 1 dimension, you'd be able to project your observables on the orthogonal subspace, on the orthogonal plane to this UF space. And then I went a step further by reducing the dimension of L prime, and in order to ensure that this transformation is surjection. And this is really important for the statistical processing that comes afterwards. This actually makes this matrix really compatible with all of the post-processing framework that we have with kernel phase. And so that's one thing that I published along with an non-sky validation of this. So for that, we observed the binary star called 3SER with the Subaru telescope at the SCIXO instrument. So here you can see the collinearity maps with the companion is really obvious here. It's an easy target for sure. But when you subtract the best fit model for this, so yeah, what I forgot to say was I do 3 data reduction pipelines, one without any form of calibration, a second with classical calibration, and the last one with this angular differential kernel approach. And so after doing a best fit binary model and removing the best fit signal, you can see that both classical and ADK have we're calibrating quite well. You can still see that in classical you have a little bit of a zony pattern here that is much less present in ADK, and to me that shows that the calibration is a bit better here, but it's better shown with the binary model fits, where you can see that the chi-square is a bit smaller here than it is here. And this is very promising for this approach. So this ADK method that I propose it remains a race in terms of calibration, just like it is in ADI, between the stability of your bias and the evolution of your signature. But it is a good alternative to classical calibration, and it would probably be very versatile, and it works both with closure phase and kernel phase. And along with what Franz published recently also in terms of a non-binary discrete model for kernels, this helps a lot in reducing improving the accuracy and the sensitivity of kernel phases. Okay, item number 2. As we've seen, we basically able to take care of speckle noise and photon noise, but just not at the same time, right? And this is really embarrassing. That's why we really wanted to play with this idea to fix the broken convolution relationship that we have in coronagraphy. But we wanted to try it with a case where it's not as bad. And for that, we played with saturated images where the core of the PSF is a little bit saturated, and that also destroys the convolution relationship. So for that, we used archive images from the Hubble Space Telescope. This is the example that I showed you earlier, so that it's Gliese 494. It's a red dwarf binary, which was not actually detected on these images at first. And so you have 4 saturated pixels here, and you can use the rest of the image to, with some knowledge of the PSF, try to interpolate the pixels that you've lost. And so that's what I did. So after recuperation of the lost pixels, I extract the kernel phases that you can see here. In calibration also, there's of course the statistical process, and I build a collinearity map that you can see here, that where you have your actual companion right here, and I do a good model fitting. So here you have a separation of 1.3 lambda over d. It's really tight. The contrast is around 50 in the K band, and so it's I took this opportunity to reconstruct the orbits based on other data that was available, and the point that I produced was this one. So it's the earliest in this whole series of observation. And I was able to recover the masses of both companions with very high precision. So that was my first publication. Okay, now trying to do some photon noise suppression in the case of kernel phase. So as we've seen, it's the image mask in the coronagraphs that destroy this convolution relationship. But there are some coronagraphs that don't rely on this image mask so much. Those are your apodizing faceplates coronagraphs like this one, and shaped pupil coronagraphs like you have a shaped pupil here. Both these masks I designed to have around 10 to the 4 dark hole from 3 to 7 lambda over d on this Skexeo pupil. So the apodizing phase mask we are not going to be able to use directly in kernel phase, because kernel phase requires this small phase approximation, and this is not the case here. However, the fact that we can use not only full pupil but arbitrary pupil means that we are going to be able to use that in the kernel phase framework. So what I did was validate that thing in simulations. So this is a comparison of the two models that I've used for this simulation. As you can see, this idea of non-binary transmission in the discrete models for kernel that was introduced this year with a paper with Martina Chenal, 2020, really helps in this, providing a model that is relatively accurate here. So what I did was a simulation where I have up to 100,000 photoelectrons in the images. And I also use 15 nanometer wavefront error in the pupil plane. And based on that, I extract the kernel phases, and using the covariance, I am able to compute the sensitivity of detection tests on this data. And as you can see here on most of the, so the dashed line is 1 lambda over d, and the dotted line is the limits of the dark hole. And as you can see here, within most of the dark hole, I can get to 10 to the 3 in contrast, in most of this region. And this is with a single image. Here you can see the difference between those two, and all the red region is where you have improvements. And here are radial profiles where you can kind of see that if you want to go to 10 to the minus 3 in contrast, you'll have to, well, with the apodized pupil, the apodized image, you can get your 10 to the minus 3 almost at half the separation. So that is really interesting. This is another validation with a companion that was introduced here. And you can see that the signal to noise in these collinearity maps is higher in apodized, with the apodized image. So we did a laser cut mask for the Skexeo instrument at Subaru. This is 19 millimeter across. We installed it in the pupil plate, in the pupil plane wheel at the instrument, and we started getting on-sky images. This is an image of Vega, but we had pretty poor conditions. But we also had a lot of technical problems. So this is me trying to fix the C-RED 1 camera that we had there with my soldering iron up at the Nasmith platform. So it was really quite an adventure, and with all the different things that happened recently, we were not able to get a real validation on Sky of this performance. And there was also something else that changed the deal and that made me kind of work on something else, and that was the appearance of the idea of kernel nulling. So this was introduced by Martina Chenal in 2018. And this was the idea of a nulling combiner for telescope, and especially for VLTI, that would combine removing the starlight and producing robust observables. And so that was really, really interesting, and I couldn't resist to try and work on this. And so, but to explain what this is and how this works, I'm going to first introduce Knurling Interferometry. So this is a schematic for a very simple nuller that's called the Bracewell nuller. And to do that, you would take two input beams, two input apertures, and you would combine them, like, for example, here with this beam splitter, in order to have on one side a constructive output and on the other side a destructive output. And this would translate with transmission maps that are here, for example, for the first output and here for the second output, where you can see that on axis you do have a full transmission here, but on axis for the second output you have rejection of the light. And so that is going to work a bit like a coronagraph for an interferometer, basically. And the behavior of those you will model with matrices like that operates on the complex amplitude at the inputs. But for the sake of this study, I've developed a tool to represent these matrices and the combinations they operate in graphically. And so these represent, each of these plots represent one output, and each color corresponds to one input. And so you can see that for the first output, both inputs are combined constructively, and here they are combined destructively. And so how does this work in practice? So you, if you have an off-axis source that moves around like this on in the field of view, you would have your the signal from this source that moves around like that, and you'd have in black the combination of the two, and as a result you'd have output intensity that gives a signal here that is modulated based on how you move around here. And so that is all well and good, but the problem is, just as coronagraphs, they are really, really sensitive to input wavefront errors. So here I represent some OPD errors at each input, and here you can see the effect it has on the throughput on axis. And so this, as you can see, there is some significant leakage light from the star that appears at the dark output. And when you combine the two, you can see that you're trying to recover your astrophysical signal, which is this dashed line, with only what you can measure, which is this really noisy observables. And so this is the solution that was proposed by Frans Martinash and Mike Ireland. So you take, instead of taking only two, you take 4 inputs, and you're going to build and you're going to have one bright output and 6 different nulled outputs. And so this is the diagram that represents that. You have your bright output and your 6 different dark outputs. And the idea is that pairwise, each pair are going to be, the leakage light is going to be correlated. And therefore, by the subtraction of each pair, you are going to be something that is much more stable. That's going to be your robust observables. And you can see there, I'm using the exact same wavefront error here. And you can see here that the leakage light is pretty much correlated and moves about like in a very similar way. So like here, you have each time 2 plots superimposed. And so the subtraction of this pair is going to give you something that is much, much more stable here. And that is also something that you can see here in these bar graphs, the raw outputs and the kernel outputs, which is in green here. And in terms of off-axis signal, however, the things are pretty much decorrelated. And so you are going to have, with a signal moving around here, you are going to have some different signal on each. And so your differential observables here are going to be significantly present. And for the same plots as earlier, you do have in the raw output something that is really noisy. But as soon as you subtract the pair together, you are recovering a lot of your signal to noise ratio. So what was my contribution with all this? My contribution was first to use these plots to understand better what's happening there. And the first thing that I noticed was you actually have those two are symmetric, like they are a mirror image of each other with respect to, in this case, the real axis. Okay, and it's true for each pair. And so in this case, they are complex conjugates of one another. And when you use this property, you can actually demonstrate all of the nice properties of robustness that I've talked about. So not only pure small phase aberrations, but also pure amplitude aberrations. So that's really interesting. And not only that, but I was also able to build these kinds of nullers for an arbitrary number of inputs. So here you can see for 3 telescopes here. So you have this symmetry once again. And also I went up to 6 apertures. That's the kind of nuller that you would use, for example, for the Chara array. And here in this case, it produces 10 robust observables. That's the most that you can get. And so that was published really recently in this paper. And so what's been done in Nice was trying to put together some of these kernel nullers in integrated optics chip. So this is one of the layouts for the 4 input ones, and just underneath here you cannot see it, but we've also used some of the three input prototypes. So this chip is we are weighting them in Nice very early, and so the chip has been manufactured. They should be bonded now. We are waiting to get them. And so they're going to be tested on this kernel bench that they have in Nice. Yeah, so to summarize my contribution throughout this project, first of all, I proposed a new method for calibration inspired by angular differential imaging. Then I played around with the idea of recovering saturated data that works very well for archive images. And I measured the masses of Gliese 494AB. I proposed to use shape pupils to modify the point spread function of the instrument and improve the photon noise performance of the kernel phases. And finally, I investigated and proposed a demonstration and a generalization for the concept of kernel nulling. And now finally for the perspectives, there are still some work and ongoing progress with physo interferometry, masking interferometry, and kernel phase in general. So there's still some progress to be made here. And in terms of more groundbreaking future improvements, we are looking towards the kernel nulling. This is really interesting because the long baseline interferometry facilities are now equipped with good fringe tracking that allows to use the nulling techniques. There are availability also for statistical data reduction method like nulling self-calibration and these robust observables that are provided by kernel nulling. And also the availability of integrated optics that enable the building of very complex combiners in a very small and stable package. So that's going to be really, really exciting. And so I'm really happy to be here to work for the sci-fi projects and maybe also a little bit with the life projects and work to bring to the sky some of these nulling solutions. Thank you very much for your attention, and I would welcome any comments or questions on everything I said.
Thank you, Romain. If people have questions, please let me know in the chat, and then I will call you out one by one if you have questions. Jacques?
Yeah, hi, Romain. So thanks for the talk. I was wondering, because you mentioned the fringe trackers. So what fringe tracker are you going to be using for the Knurling instrument on the VLTI?
So I think the idea currently is to use is to start with gravity as a fringe tracker, but there's also this idea of having this Heimdall module in this the Asgard platform that would provide probably higher sensitivity and higher precision in the in a way that could be that could provide improved performance for us. Both because it would also be closer to the final combiner, but also like the FISO combination that that is proposed for this is, should provide a better performance.
Any other questions? Denis?
Yes, thank you, Romain, for the presentation. Just wondering about the throughput of the kernel knurling chip. Do you have new measurements about that?
So the kernel knurling versus double Bracewell architecture is actually I have a slide that can show that. Yeah, so you have two different. There are two different things. The first one is the technology of the chip itself, and all that is linked with the material that you're using for combining, and also dependent on the wavelength that you're using. So in NIST, they are working on an H-band prototype because it's much easier to manufacture things for that band. But in theory, there's also a difference in throughput between what I show here. So the double Bracewell here and the kernel nuller here. So the thing is, with double Bracewell, you produce one pair of these robust you produce one robust observable, let's say, and in kernel nuller you produce three. But in terms of flux, if you consider as reference the flux of a single pupil, you would be basically have half of the throughput. So yeah, I mean, you get 3 times the observables, but you get half of the throughput. So I guess this will end up in a battle in the read noise, I guess, probably. And also in terms of, like, it's really dependent on probably what you expect in your observations. For a very simple scene, for example, when you have only one planet, you can probably figure it out with a single observable. But if you're not sure and you maybe expect a number of planets, or you don't know where it is, maybe there'll be a very important improvement with kernel nuller that provides 3 outputs.
Okay, if there are no more questions, which I see none appearing in the chat, then we thank Romain for your presentation, and I hope to see you all next week for the next seminar. Bye.
Thank you very much for your attention.
Bye.